Okay, welcome back, Chemistry 30. This is the second part of the 17.1 booklet. So activation energy, in order for the reactants to go through that transition state in which they form the activated complex, this hill that they have to overcome, or this energy required, is called the activation energy. You can think of it as the energy required to activate, sometimes symbolized as EA for activation energy. The minimum amount of energy reactants must have to form the activated complex. So if that is you can think of it as a mountain too. If it's a high mountain, that's a lot of energy. If it's a low mountain, it's a low energy. So high activation energy means it's going to be a lower rate because it takes longer to surpass that barrier. Whereas if it's a lower EA, it's going to be a high rate because it's easy to meet the activation energy requirements. Okay? So now looking at some more examples of these curves. I think you have one that looks something like this. Yours is likely neater. So we have reactants going to products. So just labeling a few things here. Number 1 here, from 0 to where the reactants are, that represents the energy that the reactants have. In particular, the potential energy. If we look at number 2, it's from here to here. So it's the energy that the reactants must get, the activation energy of the forward reaction. So in order for reactants to form an activated complex, they have to overcome that barrier. 3, it's from 0 to where the activated complex is, so that represents the energy of the activated complex, or potential energy. 4, it's the difference between where reactants are and products are. We talked a lot about this last unit. The difference between products and reactants is the heat of the reaction, the enthalpy of the reaction. And in our case here, we're going from lower energy reactants to higher energy products, so it's endo, requires the absorption of heat. And lastly, going back, number 5, it's the difference between products and activation energy. If I was to do this reaction in reverse, it would be the activation energy of the reverse reaction. Okay? Looking at this one, maybe I'll just pause the video and see if you can figure out what 1, 2, 3, and 4 are when we have reactants A and B coming together to form C. Okay, if you had a chance to do that, number 1, of course, represents the potential energy of the reactants. 2, the difference between where reactants are and activated complex, that's the activation energy of the forward reaction. The difference between where the reactants are and the products, it's the energy that's released in this case, so it's an exothermic reaction, negative. And lastly, number 4 is the energy that the products have. So potential energy of products. And yeah, I added an extra question just simply saying that, yes, it's exothermic because delta H is negative, it's going down. Okay, one more. This one's kind of the reverse of the previous one. Number 1, we're going from where the reactants are to where the activated complex is, so that's the energy required to activate the reaction, or activation energy. The potential energy of the products is number 2. You can see it goes from 0 to where the products are. 3, the difference between where the reactants are and the products. Looks like in this case we have to add energy in to reach these high products. So it is change in enthalpy, which is positive or endothermic. And lastly, number 4, from 0 to where the reactants are, potential energy of reactants. Okay, so there we have those diagrams. So we just have this left. If A is going to B, and if it's exothermic, such as this, A high is high energy for A, low energy for B, this little curve to overcome the activation energy. How does the activation energy of the forward reaction compare to the activation energy of the reverse reaction? So you can see here that the activation energy would be very small for the forward reaction, but very big for the reverse reaction, if we could do it in reverse. Okay, so there we have it. So some of the vocab terms here. Reaction rate measures how fast a reaction occurs, so change in some quantity over change in time. Looking at collision theory, in order for a reaction to occur, particles not only need to collide, but they have to collide the right way or orientation. and they have to have enough energy. So you can't put a puzzle together without using force to move the pieces around and also orientating them the right way to get the picture. Activated complex, the short-lived molecule formed when reactants collide. The transition state, it's this region in which the activated complex exists. It's not reactant, it's not product, it's some sort of intermediate state. Activation energy, the minimum energy that reactants need to have to make the activated complex. And that's it. So that's 17.1 booklet. Hopefully we see you soon for 17.2.